Hello everyone and welcome to this video. As part of the 3rd National Conference on Materials Science and Engineering, I would like to present my work entitled Modeling Hexavalent Chromium Adsorption Using an Innovative Waste Product, Sunflower Seed Shells, in Dynamic Mode. Water is considered a fundamental element of human life and activity. It is a major component of both the mineral and organic worlds. In today's world, we use water for all kinds of purposes including domestic, industrial and agricultural, making it a receptor element exposed to all kinds of pollution. In this context, several models have been developed, such as the Thomas, Yoon Nelson, Bahart Adams and Wolborska models. These mathematical models are more realistic and make it easier to predict breakthrough curves as a function of the conditions studied. Sunflower seeds are used to produce oil and flour, but the shells are an unused waste product that is often burnt or left to rot in the fields. The hull is made up of cellulose, lignin and hemicellulose fibers, and represents between 20 and 30% of the total seed biomass. Shell proteins and lipids are present in small quantities. Many researchers have focused on using this waste product in various applications such as animal feed production, food alloys, hydrocarbons, energy production, insecticides, ceramics, as a corrosion inhibitor, in the adsorption of heavy metals and organic compounds from wastewater, etc. As regards materials and methods, the sunflower was collected from the local market and shelled to recover the shells. To remove impurities, the material was washed several times with water, then with distilled water, then dried in the open air and in an oven at 105 degrees Celsius for 24 hours to eliminate residual moisture. In an electric mill, the sunflower seed shells were ground and then sieved. Only particles with a diameter of less than 315 micrometers were used for experimental adsorption tests. The 4 mathematical models were applied to different parameters influencing adsorption such as flow rate, height, hexavalent chromium concentration, sodium chloride and temperature. The results obtained are illustrated in the figures in front of you. Figure 2 represent theoretical and experimental penetration curves at different flow rates for hexavalent chromium adsorption by sunflower seed shells. Under conditions of bed height 20 mm, pH equal to 1, temperature of 298 Kelvin and hexavalent chromium concentration equal to 10 ppm. Figure 3 represent theoretical and experimental penetration curves at different bed heights for hexavalent chromium adsorption by sunflower seed shells. Under conditions of pH equal to 1, temperature of 298 Kelvin, hexavalent chromium concentration equal to 10 ppm and flow rate of 2 ml by minute. Figure 4 represent theoretical and experimental penetration curves at different hexavalent chromium concentrations for hexavalent chromium adsorption by sunflower seed shells under conditions of bed height 20 mm, pH equal to 1, temperature of 298 Kelvin and flow rate of 2 ml by minute. Figure 5 represent theoretical and experimental penetration curves at different pH for hexavalent chromium adsorption by sunflower seed shells under conditions of bed height 20 mm, hexavalent chromium concentration equal to 10 ppm, temperature of 298 Kelvin and flow rate of 2 ml by minute. Figure 6 represent theoretical and experimental penetration curves at different sodium chloride concentrations for hexavalent chromium adsorption by sunflower seed shells under conditions of bed height 20 mm, hexavalent chromium concentration equal to 10 ppm, temperature of 298 Kelvin and flow rate of 2 ml by minute. And Figure 7 represent theoretical and experimental penetration curves at different temperatures for hexavalent chromium adsorption by sunflower seed shells under conditions of bed height 20 mm, hexavalent chromium concentration equal to 10 ppm and flow rate of 2 ml by minute. In conclusion, mathematical models are more realistic and enable better prediction of breakthrough curves under the conditions studied. They are also very useful for the design of adsorption columns, as they can be used to determine column dimensions such as height and diameter, and the best operating conditions. Mathematical models are based on mass balances in the liquid and solid phases, depending on the kinetics governing adsorption. The two balances, liquid-solid phase, are linked by the equation that best describes the adsorption equilibrium. Thomas and Yoon Nelson models from the results obtained It is interesting to observe that the correlation coefficient values of both the Thomas and Yoon-Nelson models are greater than 0.95. This is verified for all the parameters studied. Similarly, the adsorption capacities and tau values calculated and the value obtained experimentally are quite close. The Thomas and Yoon-Nelson rate constant increases with increasing flow rate, but tau decreases accordingly. This is due to the driving force of adsorption and the fact that a higher flow rate allows adsorption equilibrium to be reached quickly. It can be stated that both models studied are suitable for describing hexavalent chromium adsorption by sunflower seed shells. Bahart Adams and Wolborska model. According to the results obtained, the values of the kinetic constant of the Wolborska model turn out to be influenced by all the parameters studied. This shows that external mass transfer in the initial part of the sorption process dominates the system. Due to the predominance of external mass transfer activities, the mass transfer coefficient increases with increasing flow rate. The parameter beta underscore reflects the effect of mass transfer in the liquid phase and axial dispersion. An increase in flow rate from 1 to 3 milliliters by minute improved the value of beta underscore A because the increase in turbulence reduces the boundary of the film surrounding the absorbing particle. The values of N0 calculated by Bahart Adams and Wolborska, and the values obtained experimentally are sufficiently far apart. Furthermore, based on the superposition of the experimental results, dots, and the calculated theoretical points, lines, it appears that neither breakthrough nor overall failure curves are well predicted by these two models. It can be stated that the two models studied are inadequate for describing hexavalent chromium adsorption on sunflower seed shells. In order to achieve a healthier environment, the main aim of this thesis is to demonstrate the value of using nature's abundant bioadsorbents in the treatment of liquid effluents. To achieve our objective, we have focused our study on the behavior of sunflower seed shells as innovative and economical bioadsorbents. 5 mathematical models were used to describe the fixed bed system. The Thomas, Yoon-Nelson, Bahart Adams and Wolborska models all gave good approximations of experimental behavior, with the exception of the Bahart Adams and Wolborska models. Finally, thank you for your attention to this presentation.